We're going to conclude our work on series by looking at the difference method, or the method of telescoping series. So let's start with an example. We're going to consider the sum between 1 and n of r plus 1 factorial take away r factorial. Now, using our properties of sigma notation, we can straight away say that that's the same thing as the sum between r equals 1 and n of r plus 1 factorial, take away the sum between r equals 1 and n of r factorial. So if we consider the first of these two sums, what we've got there is going to be, first of all, 2 factorial, then 3 factorial, then 4 factorial, all the way along to n plus 1 factorial. Whereas then the second term is just going to be 1 factorial plus 2 factorial plus 3 factorial all the way up to n factorial. Now if we look carefully, we can see that lots and lots of the terms are going to cancel there. The 2 factorial at the beginning of the first bracket is going to cancel with the 2 factorial, which is the second term in the second bracket. Similarly, the 3 factorial in the first bracket will cancel with the 3 factorial in the second bracket. The 4 factorial and the 4 factorial will cancel. And that happens all the way along until we hit the n factorial in the first bracket, cancelling with the n factorial in the second bracket. And in fact, there are only 2 terms there that haven't cancelled out. And we're left with the n plus 1 factorial from the first summation, take away the 1 factorial from the second summation. So that rather complicated summation that we had, by expanding it, we realised that nearly all of the terms cancelled out, and the whole series cancels down, or if you like, telescopes down, to just give me n plus 1 factorial, take away 1 factorial, and we know that 1 factorial is 1, so I can say it's n plus 1 factorial, take away 1. Now this is an example of what we know, what I call at any rate, a telescoping series. When the series is written out in full, almost everything cancels out just to leave a few terms. It's worth noticing that in terms of seeing the cancelling out, it's well worth trying to line things up so that the similar terms lie one above the other. So let's move on to a second similar example. We're going to consider the summation between r equals 1 and n of the natural logarithm of r plus 1 divided by r. Now, using the properties of logarithms, we know that the natural logarithm of r plus 1 divided by r is exactly the same thing as the natural logarithm of r plus 1, take away the natural logarithm of r. Using the properties of sigma notation, we can now split that up and say what we've got is the sum between r equals 1 and n of the natural logarithm of r plus 1, take away the summation between r equals 1 and n of the natural logarithm of r. Now, if we expand the first summation starts with natural logarithm of 2 plus the natural logarithm of 3 plus the natural logarithm of 4 and goes all the way along until we reach the natural logarithm of n plus 1. Whereas the second summation starts with the natural logarithm of 1 plus the natural logarithm of 2 plus the natural logarithm of 3 and goes all the way along until we reach the natural logarithm of n. Notice how I've written this out to try and make the cancellations really obvious. We've written the similar terms in the second summation immediately above the similar terms in the first summation. So looking at what we've got, we can see we've got a logarithm of 2 in the first summation cancelling with logarithm of 2 in the second summation. Similarly, we've got logarithm 3 in the first cancelling with logarithm 3 in the second. We've got logarithm 4 in the first cancelling with the logarithm of 4 in the second. We've got logarithm of n in the first cancelling with logarithm of n in the last. So almost all of the terms have cancelled out yet again, and all we're left with that hasn't cancelled out is the logarithm of n plus 1 from the first summation, take away the logarithm of 1 from the second summation. So we've got there logarithm of n plus 1, take away the logarithm of 1. But of course the logarithm of 1 is just 0, so that is therefore the logarithm of n plus 1. Now in our next example, we're first of all being asked to express 6 over r plus 1 times r plus 2 as a sum of partial fractions, and then we're going to use the result to try and find the sum of a series, and finally deduce the value of the sum to infinity of a series. So concentrating on the first part to begin with, we've got to express 6 divided by r plus 1 times r plus 2 as a sum of partial fractions. Now if you've not met partial fractions before, you need to ask at this stage your teacher to give you access to the video on partial fractions, which is in the Mathematics Unit 3 set of videos. Okay, if we've got 6 over r plus 1 times r plus 2, then that's likely to have come from a fraction, split fraction of the form a over r plus 1 plus b over r plus 2. Now we need to find out what a and b are, and to do that we are going to multiply each side of the identity by the common denominator of the left-hand side. In other words, we're going to multiply each side of the identity by r plus 1 times r plus 2. If we do that, we're going to obtain 6 on the left-hand side must equal a times r plus 2 plus b times r plus 1. Now, this identity needs to be valid for all possible values of r. And if we're careful over the choice of the values of r, we can find a and b very easily. So if I put r equal minus 2, then the value of the left-hand side is still 6, but the right-hand side simplifies to a times 0 plus b times minus 1. In other words, I've got 6 equals minus b, which means that b must be minus 6. Similarly, if I put r equals minus 1 in, the left-hand side is 6, and I've got 6 equals a times 1 plus b times 0. In other words, a must be equal to 6. So I now have my split up of 6 over r plus 1, r plus 2 is the same thing as 6 over r plus 1 plus minus 6 over r plus 2. In other words, 6 over r plus 1 minus 6 over r plus 2. So we've done the first part of the question. We've now got to simplify the sum between r equals 0 and n of 6 over r plus 1 times r plus 2. Now we've just found out that 6 over r plus 1 r plus 2 is the same as 6 over r plus 1 take away 6 over r plus 2. So, using the properties of sigma notation, I can split that up as being the sum between r equals 0 and n of 6 over r plus 1, take away the sum between r equals 0 and n of 6 over r plus 2. And if we write this out longhand, then the first summation starts off with 6 over 0 plus 1, so that's 6 over 1. Next term is going to be 6 over 1 plus 1, so that's 6 over 2. And the next term is going to be 6 over 2 plus 1, so that's 6 over 3. All the way along until the final term there is going to be 6 over n plus 1. And then the subtracted sum, when we put r equals 0, is going to be 6 over 0 plus 2, so that's 6 over 2. When we put r equals 1, it's going to be 6 over 1 plus 2, so that's 6 over 3. And it's going to go all the way up until we reach 6 over n plus 2. Now again, we've written things out carefully so that the terms in the second expansion, which are similar to terms in the first expansion, lie immediately underneath, which means that we can make the cancelling occur nice and easily. So we can see the 6 over 2's cancel, we can see the 6 over 3's cancel, we can see the 6 over 4's cancel, all the way along until the 6 over n plus 1's cancel. So all I'm left with that hasn't cancelled is the 6 over 1 in the first bracket, then take away the 6 over n plus 2 from the second bracket. So again, the series has telescoped down really nicely for us. So we've got the sum between r equals 0 and n of 6 over r plus 1 times r plus 2 is 6 minus 6 over n plus 2. Moving to the final part of the question, we've got to deduce the value of the sum between r equals 0 and infinity of 6 over r plus 2. Well, the sum between r equals 0 and infinity of an expression is always defined as being the limit as n tends to infinity of the sum between r equals 0 and n of that expression. We know that the sum between r equals 0 and n of 6 over r plus 1 r plus 2 is the same thing as 6 minus 6 over n plus 2. So what we're after is the limit as n tends to infinity of 6 minus 6 over n plus 2. As n tends to infinity, 6 over n plus 2 becomes very, very small. It gets very, very close to 0. So the limit that we're looking for is simply 6. So the sum between r equals 0 and infinity of 6 over r plus 1 r plus 2 is equal to 6. And to finish this video off, just pause it again and have a go at this question